Before we get started, let's set up the scene so that you know where we're at with our learning journey, what you have learned from the previous lessons, and what you're going to learn today, and what's coming up in the next lessons. In the previous lessons, we explored the following concepts. Defined image noise as unwanted static that interferes with the clarity of a photo, making it look grainy, speckled, or blurry. We explore the cause of image noise. They can come from camera sensor limitations, such as dim environments, high ISO settings, thermal activities inside the sensor, or electronic interference. It could also come from transmission issues, such as data compressions resulting in data loss, or limited network bandwidth in video streaming. We learned that modern smartphone cameras automatically apply denoising techniques using advanced AI models like convolutional neural networks, or CNNs for short, to recognize and remove noise patterns. We had a quick introduction to feature extractions, which is the fundamental process where AI understands and simplifies important parts of an image by picking out details like edges, texture, or shapes, rather than focusing on every single pixel. We also looked at convolutional layers, which is the core building blocks that help the network see and understand images. Learnable filters. The convolutional layers apply learnable filters, which are like small magnifying glasses or templates that slide over the image to find specific patterns. Filters. Each filter is a small grid with numbers called weight or parameters. Weights. These values are learned during training and determine how the filter responds to specific patterns like edges, corners, or textures. The goal is to adjust each weight in the filter grid to optimize the CNN's ability to detect meaningful features. Built on that foundations, today we'll dive into the CNN training process. Understanding the CNN training process is crucial because it is critical for our understanding of machine learning in general and convolutional neural networks specifically. As mentioned in the previous lessons, filters in the CNNs are not manually designed, but are learned automatically during training. Therefore, understanding how training works helps us see how the CNN develops the ability to identify meaningful features in noisy images. Feature extraction, which is the first step of the 4-step AI denoising process, relies on the CNN's ability to learn relevant features through its training process. Therefore, understanding the training process provides you with the transferable framework for how neural networks learn in various domains. Concepts like backpropagations, gradients, and loss functions are universals in deep learning, making this knowledge broadly applicable. In today's lessons, we'll explore the following concepts. Training dataset. The training process begins with filters initialized with random weight values, and the model is fed a dataset containing pairs of noisy images and their corresponding clean, ground truth images. Backpropagations, which is the core learning algorithm. Backpropagations is the key algorithm used to train neural networks like CNNs. Its purpose is to adjust the weights of each filter to minimize prediction errors. It's about understanding backpropagation, which is the process of adjusting filter weights based on errors calculated by a loss function. We see how errors in the final output, the denoise image in this case, guide the refinement of filter to optimize feature extractions. Calculating error with the loss functions. The CNN processes a noisy image to produce a denoise output, and the errors is quantified using a loss functions. This function measures the difference between the network's predictions and the desired ground truth, which is the clean image. Addressing a common misconceptions. We're going to clarify that the error is not calculated by comparing features detected by filters, like edges or textures, to predefined features. Instead, these features are learned implicitly to optimize the final output. Understanding this misconception about error calculation is essential because it clarifies how CNNs learn feature automatically, distinguishing CNN from the traditional image processing method. And it also ensures you grasp the mechanics of backpropagation and feature extractions. Traditional image processing versus CNNs. Unlike traditional method where filters are manually designed, CNN filters are learned automatically. Training versus inference. Once trained, the filter weights are locked for inference, which means processing new unseen images. And backpropagation is not active during this phase to ensure performance on devices like smartphones. Output level error calculations. Errors is calculated by comparing the CNN output image to the clean ground truth image. The mean square errors, or MSE for short, is the common loss function used for this purpose. Gradients and weight updates. The calculated error is propagated backward through the network to compute gradients for each weight. A gradient indicates how much a small change in the weight affects the loss and in which directions. Once the CNN training context is set, after these lessons, we learn the fundamental principle of a CNN by looking at its mathematical definitions, its brief history of convolutions, key components of convolution, and convolutions in the context of CNNs for image denoising. So we have learned from the previous lessons that most modern smartphone cameras automatically apply denoising techniques when capturing photos, especially in challenging conditions like low light or high ISO settings, and that's the whole process takes place in the matter of milliseconds. But what is actually happening inside your phone in that split second? How does it know what a clean photo is even supposed to look like? You'd probably guess that the AI had some kinds of, a reference library, right? Like a dictionary for the perfect sharp edges and smooth texture that it just, copies and pastes over the ugly parts. And that seems logical, but that's not what's happening. The reality is way more fascinating, and it all starts from a place of knowing absolutely nothing at all. So here's our roadmap for these lessons. We're going to start with the AI very first day on the job. Then we see how it learns from a master, how it figures out its own mistakes, and the incredible way it corrects them. We'll watch it go from a total trainee to an expert. And finally, we see how this whole approach is such a massive game changer. Okay, let's meet our brand new AI model. It is a type of neural network called a convolutional neural network, or CNN for short. And on day one, it is completely and utterly clueless. The core of this AI, its brain, if you will, is made of this thing called filters. But when it's just starting out, the filters are basically clueless. They are just grid filled with totally random numbers, what we call weights. It's a completely blank slate. It has no concept of an edge, a color, a texture, or shape. So how does a completely useless AI get smart? Well, you send it to school. And its classroom is a gigantic library of pictures taught by a very particular kind of teacher. Its whole educations come from this massive dataset of image pairs. On one side, you got the test. That's a photo that we've intentionally made it noisy and ugly. And on the other side, you got the answer key, the original, perfectly clean version of that exact same photo. We call that perfect version the ground truth. The AI one's and only job is to figure out how to turn the test into the answer key. So the AI takes its first guess. It shoves that noisy image through all its random filter and spit out, well, probably garbage at this point. Now comes the single most important step, figuring out just how wrong it was. This is its uh-oh moment. This is handled by a clever bit of math called a loss functions. You can think of it as the ultimate critic, or as a scorekeeper. It takes the AI garbage output, compares it pixel by pixel against that perfect ground truth image, and boils all of the difference down into a single number, the error score. For denoising CNN, the mean square errors, or MSEs, is a common loss function used to calculate the average square difference between the predicted and actual pixel values. A giant score means a total failure. A score close to 0 means it's getting warmer. And this right here, this is where we bust that myth we started with at the beginning of the video. The loss function doesn't care one bit if the AI makes a good edge detection here or a nice texture there. It is totally blind to the process. It's only look at the final finished picture and ask one thing. How different is this from the perfect answer? That's the key. The AI only learns to find things like edges and textures because it needs to, as a side effect of its one single goal, which is to make that final error score as tiny as possible. This misconception, which is the belief that errors is calculated by comparing intermediate features such as edges, corner, etc., to predefined patterns, rather than comparing the final output, which is the denoise image, to the ground truth clean image. This misconception suggests that CNNs rely on manually predefined features for error calculation, which undermines the key strength of CNNs, which is their ability to automatically learn relevant features through training. This clarification solidifies the understanding that features like edges or textures are intermediate representation only, learned implicitly to minimize the overall loss, and not compared to predefined patterns. This is crucial for appreciating the data-driven nature of CNNs. Additionally, feature extraction involves filter learning to detect patterns like edges or textures through training. If error was to be calculated by comparing these features to predefined patterns, we might have assumed feature extraction is a rigid, human-defined process rather than a dynamic learned one. This is crucial as it ensures that we understand how feature extractions enable the CNNs to adapt to diverse noise types without relying on fixed rules. Okay, so the AI has its big fat error score. It knows it messed up, but how does it use that one number to fix the millions of tiny random ways inside its filters? This is where the real magic happens. It takes a backward journey, a process called backpropagation, which is a key algorithm used to train neural networks, including CNNs. It takes one final error score and sends a signal all the way back through the entire network. It's like a coach reviewing game film, but on an incredible scale. It doesn't just tell the team you lost. It goes to every single player, or every single filter in this case, and shows exactly how its specific actions contributed to that final terrible score. And this whole thing becomes a powerful learning loop. The AI makes a guess. The loss function scores its failure. That error gets sent backward through the network. This backward trip calculates something called a gradient for every single weight, and then all those weights get a tiny update. And it immediately tried again, just a tiny bit smarter this time. So what is this gradient? Well, think of it as a personalized coaching tips for every single one of those millions of numbers inside the AI. It's a specific targeted instruction. It tells one weight, hey, you need to be a little bit higher. And then it tells another weight, you need to be a little bit lower. All in the service of getting a better score on the very next attempt. So what happens when you let that learning loop run not just once or twice, but millions upon millions of times? Well, that's when our clueless trainee finally become a master. After all that trial and error, all that feedback and correction, those filters that started out as random digital junk have been slowly shaped and molded by the data. They aren't random anymore. They have automatically transformed into highly specialized tools, expert detector for the exact kind of patterns that are actually useful for telling image details apart from ugly noise. And that brings up a really crucial difference: training versus inference. The training part, all that learning and backpropagations, is a slow, heavy-duty process that requires powerful computers for processing. But once the AI is an expert, we lock the filter in place. That's the inference phase, which is a lightweight, lightning-fast version that actually lives on your phone, ready to work its magic instantly without having to learn anymore. If the model needs to be retrained for improvement, software updates that include entirely new or improved CNN models will be released for the user to install at their convenience. Now, this whole method of learning might seem a bit complicated, but it is a revolutionary break from how we used to build things like this. It really does change everything. You see, in the old days, a human engineer would have to literally sit down and hand code a filter to do one specific job, like finding a 45-degree angle edge, for example. It was incredibly rigid and tedious. With these neural networks, and specifically with CNNs, we don't do any of that anymore. The AI learns its own filter, perfectly tuned for the job, just by looking at millions of examples of the test and the answer key. And that right there is the bottom line. The most crucial takeaway is that we don't teach the AI how to see. We don't give it a rule book or a dictionary of features. We simply show it what a correct final picture looks like, and we create a system where it can endlessly experiment and correct its own mistakes. We give it the destination, and the AI teaches itself the way to get there. It's a really powerful idea, isn't it? You have now mastered a comprehensive understanding of the convolutional neural network training process. This understanding is crucial for grasping machine learning in general, and CNN specifically. Here's what you've just learned in today's lesson. Filters in the CNN are not manually designed, but are learned automatically as part of the training process, enabling the CNN to identify meaningful features in noisy image. The training process begins with filter initialized with random weight values, and the model is fed a dataset containing pairs of noisy images and their corresponding clean ground truth images. Backpropagation is the key algorithm used to train neural networks like CNN. Its purpose is to adjust the weight of each filter to minimize prediction errors. This involved input data, producing an output, loss calculations, error propagation backward, layer by layers, gradients computations, and weights updates using an optimization algorithms like gradient descent. The CNN processes a noisy image to produce a denoise output, and the errors is quantified using a loss functions. This function measures the difference between the network's predictions and the desired ground truth, which is the clean image. For denoising CNN, the mean square errors, MSE, is a common loss function used to calculate the average square difference between predicted and actual pixel values. The calculated error is propagated backward through the network to compute gradients for each weight. A gradient indicates how much a small change in a weight affects the loss and in which direction, whether to increase or decrease the weight to reduce the loss. Having established the context of CNN training, the next step will be to explore convolution itself, including its mathematical definitions, historical context, key components, and its specific application within CNNs for image denoising. Understanding this is crucial, and it is the fundamental principle of a CNN itself.